Yeah. Hi everyone. This is Rishwant, and I'm doing this video to explain the element distinctness problem. So this problem is given to me by instructor Dr. Sharma Tankachan, like to prove the lower bound for element distinctness problem. So basically, the problem statement is that. If there are n elements in a given array, so we have to find the distinctness between the elements in an array. So we have like two solution: either the elements are distinct or not distinct. So we are taking it in an yes or no manner. So let me just take an example saying that for the first one, you could see that all for the first one, you could see that all elements in an array are distinct. So the output for this algorithm should return yes. And if you see this second array, there are two distinct elements. There are two elements which are same in the array. So the output should return no. So basically, the trivial solution for this algorithm will be O of n square. For example, if we take this same array 1, 7, 4, 9, 3, so basically the trivial solution will be O of n square. Why? Because it's like will compare each and every the one like each and every element with the other element, and we'll do the same for the rest of the elements. So this is not the effective way to do it. So one effective way is first we'll sort the elements in an array. So for sorting, it will take uh, n log n, and for adjacent elements comparison, it will be n minus 1. So total time complexity for this is O of n log n. Like what we are proving in this problem statement is that we have to prove the lower bound for element distinctness problem to be big omega of n log n. So let's try to prove the lower bound for element distinctness problem to be omega of n log n. Yeah, that's it. Okay, so let's try to prove this omega of big omega of n log n using sorting lower bound. So we can let's try this using decision tree. So this is a sample decision tree which I have taken. So first let's discuss about what's decision tree consists of. So everything which is circled here, we call this as nodes, and each node has its different tails, and for this decision tree, like all edges are used to compare between nodes, each and every node. So for example, I have taken an example of array 175. So basically I'll take this as an index 1, index 2, and index 3. So which I have labeled here 1, 2, 3, everything I'm referring to the indexes. And now if I try to prove the time complexity for this decision tree, so what I'll try to do is I'll place the first and second index in here, and then I'll try to check whether if it is less than or greater. So by this through this array, we can observe that we'll get output 157 in this manner. So this one and this one and this way. So basically every decision tree has leaf nodes leaf node as its is the last point of a decision tree. So for this array, we have six leaf nodes if we consider this decision tree. So basically, the number of elements, if there are n elements in an array, the number of leaf nodes count will be n factorial. So in the above example, if you could see, I have taken three elements in an array. So I have got 6 leaf nodes in here. So basically for n elements in an array, we'll have n factorial leaf nodes. So if I try to find the time complexity of this decision tree, I have like, I have first, if I check the height of the tree, so the height of the tree will be n log n factorial. So which means it will be omega of n log n, the time complexity. So, but for element distinctness problem, we have like only two solutions, either yes or no. So if we try to prove it using like prove this decision tree, like sorting lower bound using this log n thing. So we have like only two solutions, log 2 factorial, which is basically 1. So basically we have only one method to prove that prove this element distinctness problem, so which is not true. So let's try using an effective way. Yeah, that's it. Okay, so now I'm going to try to prove the like main theorem T of n equal to omega of n log n in a new approach. So for my new approach, for example, I'm taking an x instance which consists of coordinates like from x1, x2 till xn. So these coordinates point in n dimension space, so where we restrict the instance, this respective instance in unit to unit and cube, so that every coordinate in this x instance should lie between 0 to 1, just because so that we can interpret the values in a easy manner. So for example, it's hard to portray if you take n number of instances, it's difficult to portray them in n dimensions. So for our convenience, I have taken just 2 dimension. So I have taken 2 dimension to explain. So for example, if you take a sample point like 0.70, so that point lies in this region. Or let's take an example like 0.7 comma 0.2, it might lie in this region. So if I take one more point like 0.1 comma 0.8, it might stay in this region. So if I take an example, like if you see here, all the elements in this array are distinct. So if I take an example like 0.5 comma 0.5, so this might stay in at this point of time, like in here. So if you see here, the elements in this array are not distinct. So whenever any two, like in 2-dimensional space, if you take any two elements which are not distinct, so all non-distinct elements will lie in the diagonal region. Apart from this diagonal region, the elements which are distinct will lie either this above the diagonal, or either it lies below the diagonal. So I can take this as in 2-dimensional space, either above the diagonal or below the diagonal. The region I can consider it as distinct region. The points which lie on the diagonal, it will be considered as no. That means the elements in that particular dimension in that array are not distinct. Okay, so what I am going to say is that to prove this main theorem, I am taking three subclaims, so that through these three subclaims I can prove that the lower bound time complexity for this algorithm is omega of big omega of n log n. So let's take the first subclaim which I am going to prove. So which one is R of L is connected? So basically R of L, what is R of L is for every leaf node L, like we have to reach the time to reach the leaf node um, uh, till the execution of reaching the leaf node, like we have to prove that R of L is connected. And coming to second subclaim, I'm going to take two instances. One is X instance, which have coordinates like x1, x2, xn, and Y instance, which is the permutation of X instance. So, for example, if I take an example like 1, 3, 5, or 1, 5, 1, 5, 4. So, the permutation of this X array will be like different combination of my X instance. So it's just like we are going to say that these two instances must reach must find a distinct path to find the distinct elements. So in the second claim we are going to prove this, and third claim is we have to prove that number of S leaves must be greater than or equal to n factorial, so that we can prove that time complexity of this the lower bound time complexity for this algorithm should be big omega of n log n. Yeah, so first I'm going to take the subclaim one to prove that R of L is connected. So what so we have to prove that R of L is connected. So let's take a region R, which is said to be connected for any points X, Y, which belongs to region R. So there exists a path from X to Y passing entirely through X region R. So, for example, if I take some region, so I have 2 points X, Y, uh, if I take this example, X, Y, so in this case, we can say that this is not connected because it's going out of the region. For example, if I take one more region R, so in this region, so if there are 2 points R, X and Y, they are connected somehow, but not in a straight line. So basically it's difficult to prove if they are connected or not unless and until they are in a straight manner. So if they are connected in a straight line, we could say that this region has a convex region. So let's try to prove this R of L is connected in a convex manner, because as I said, straight line, it's easy to prove that R 2 points are connected in a straight line rather than in a different connected way. Basically I'm going to do the pictorial representation for R of L. So if I take a tree which has its nodes, for example, yeah. So basically, if I take uh, like uh, 3 points, like if I take a three-dimensional space which consists of points x1, x2, x3, 3 dimensions, so I can consider this as x1, x2, and then this as x3. So if we are going to prove lower bound, like if you are going to prove that R of L is connected, I mean these 3 points are connected. So as per as we saw previously, for every points in this instance, like coordinates in this instance, they must go through some sort of comparison. Okay, so if they have to go through some sort of comparison, for example, let's say that if I compare x3 with x1, let's say that x3 less than x1. So in this case, the front face which we are seeing here comes under uh, like uh, comes under x3 less than x1 region. So if we slice this x3 less than x1 graph, so this will be in a convex manner. So somehow they are connected in a convex manner. For example, if I take x3 equal to x1, so in this case, if I slice this x3 equal to x1, my point lies somewhere in here in this convex manner. So, at last, I could say that if you take any kind of condition, we'll slice the region in a convex manner. Slicing operation maintains the convex nature. If we repeat this several times for all the coordinates in this instance, then the last piece remaining in this 3D diagram will be also in a convex manner. Okay, so now we have seen the pictorial representation of how to show like RFL is connected. Now we'll do it in a more professional way by using some proof for claim one. So I'm taking two instances, for example, X and Y, which has coordinates from X1, X2 till Xn, and then Y1, Y2 till Yn. So I am going to do this in three executions, which is this is execution 1, 2, and this is the third execution. So first execution, what I'm going to do is instance X, like the coordinates in instance X will reach the leaf node in some path. So let's consider this second execution. So instance Y will reach the leaf node in the same path where x instance coordinates are reached. So if we consider execution 3, for example, if we take z as execution 3, so it has coordinates like z1 z2 till zn. So this is the straight line equation for any z of I coordinate. So uh, I am like why I have given lambda value should be between 0 and 1 is because in the above equation, if I substitute x as lambda as 0, then I'll get the only like y coordinate value. If I put that as 1, if I substitute this as 1, I'll get only x coordinate value. So to prove let us consider that this root label like I and j uh, we will start this using execution 1. So uh, for example, if I say that xi is x less than xj, so to prove this theorem, I am multiplying this by lambda, and then y coordinates, I am multiplying this by 1 minus lambda. So if I after multiplying, if I add the respective xi yi coordinates and respective I and j labels, so the output of this the line equation, the comparison will be in this manner. So from here we can say that this is the line equation for z of y and this is the line equation for z of z. So we can say that z of I is less than z of z. So which is by using the above execution 3, we proved that for example, if x is taking this path and y is taking the same path to show that s to prove s leaves, which means they are distinct elements in x and y instances. So I could say that from this proof, so z instance lies somewhere in the same path where x and y are connected. So since z instance is connected in the same path as x and y, we could say that this as a convex thing. And then from this I could say that R of L is connected in a convex manner. So connected in convex manner. So we proved that the Z instance lies in the same path as X and Y. So in a convex manner. So I can prove that claim one, which is R of L, is connected. Okay, so now we are done with proving the first claim. So coming to second claim, we have to prove that two instances. For example, let's take an example X, like instance X and instance Y. So we have to prove that both instances are reaching to the different leaf nodes in different paths. So let's consider that X instance X is reaching to leaf node L1 in some path, and instance Y is reaching to different leaf node in a different path. So our basic uh, claim is to prove that these two instances are reaching in a different manner. So to prove that, we will use proof of contradiction. Proof of proof of contradiction to prove that both instances are reaching to different leaf nodes. So in this, let us take an example like instance X and Y, which has X1 to X and Y1 to YN leaf YN coordinates. So if as per proof of contradiction, if I am for example, I am thinking that both X and Y instance are reaching to the same leaf node, not different leaf nodes. Then, so as per proof of contradiction, I am considering X and Y are reaching to the same leaf node. So in this case, if point Z like it got S leaf, then X and Y are reaching to the same node. If it is no, so then they are reaching to different leaf nodes. So through proof of contradiction, we are going to prove that Z is going through no leaf. So I forgot to mention this Y instance is nothing but permutation of X instance. I'll show you examples. I'll show you example just in a bit. So I am considering the X and Y instances are reaching the same leaf node. Let us consider the path for this reaching the leaf node as a P. So if I consider this Z instance belongs to P, so as per I am considering, for example, xi is less than xj and yi is less than yj. I am considering this subclaim just because, for example, to explain why I have claimed taken this subclaim is, for example, if I have two instances x and y, I have 1, 3, 5 as an array, and if you see here, y is an permutation of x, which means all the elements in the array are same but in a different sorted manner. So if I take this xi less than xj, this condition will be satisfied in here. But if I try to put the same condition xi less than xj, which is not true. So that is why I have taken, for y instance, I have taken proof like yi greater than yj as, okay. So this is the first thing which I have considered. And let me consider the equation f of w equal to wi minus wj. So if I substitute x in here, since xi is less than xj, I'll be getting a value less than 0 for f of x. And for f of y, since y is greater than yj, I'll be getting f of y greater than 0. So through mean value theorem, f of z will be 0. So which means zi is equal to zj. So that means both the elements are not distinct, like elements are same. So in this case, we will get no as an output. So through proof of contradiction, what we have proved is that x is reaching to a uh, like x is reaching to some node L, and then y is also reaching to the same node. But from this proof, we could see that Z is throwing the output no, which means they are not reaching to the same nodes. So from second claim, we proved that X and Y instances, I mean, the permutation of combinations are reaching different leaf nodes, so which are distinct. So coming to third claim, we are going to prove that number of S leaves must be greater than or equal to n factorial. So from second claim, we could consider that different instances. For example, if we take an X instance, it has different number of permutations for X instance. So like if there are n instances, we'll be getting n factorial permutations. So there will be n factorial S leaves, so that there will be n factorial S leaves, which means the time complexity of this n instances will be big omega of n log n. So by using these three subclaims, we proved that the minimum time complexity, by using these three subclaims, we proved that the minimum lower bound time complexity for element distinctness problem is big O of n log n. Sorry. It's omega of n log n. Yeah, that's it. Thank you.